Okay, welcome to Chapter 15. This is a podcast on chemical equilibrium. All right. This is a really important topic. It is guaranteed to be the first question in the free response section of the AP exam. So you're guaranteed to get this question, and so being really good at equilibrium is important. All right, so when you think about chemical reactions, we think about, generally we usually think about a reactant going to make a product or products, but usually what happens is it doesn't go all the way, that there is some state where the reaction stops, where you have a mixture of products and reactants. And there's actually, even though it seems like everything's done, there are forward reactions and reverse reactions happening at the same time. So there are still products being made, but there are also reactants being made from those products. And we show those equilibrium equations using double-headed arrows. Okay? So a chemical equilibrium actually occurs when the rate at which the forward and the reverse reaction are occurring at the same, are one and the same. Okay? Let's talk a little more about what that means. So if I were to take an equation, and here I'm taking a forward equation where I'm starting with N2O4 and I'm making NO2, and if I plot that time versus rate, what I'll see is that eventually these rates will become exactly the same. And at that point where they become exactly the same, we have equilibrium. Now, be careful, because this is rate here. We're talking about the rate at which they're occurring is the same, not the concentration. If we're to plot the concentration graph, what we see is, okay, so we're not quite there yet. So forward and reverse rate occurring at the same rate, okay? But if we were to plot concentration, we're not going to end up on the with the same line, right? They're not ending up at the same concentration. They're just ending up at the same rate. The rate at which the forward reaction is occurring is the same as the rate at which the reverse reaction is occurring. Okay. So if I can show you that the equation or the graph would look different if depending on what the equation is or what the reaction is, right? It could look like this. Oops. Let me make this red. Okay. It could look like this, where they're doing that, or it could look like this and like this, where they never cross, right? It's just the point at which they go flat, the concentrations go flat, is the point of equilibrium. Okay? So it's when the concentrations for both stabilize, and it's also the point where the rate at which the reaction is occurring stabilizes. Since in a system equilibrium, both the reverse and forward and reverse reactions are being carried out, we write the equation with a double arrow. Okay, and you can write it like this, or like this, which is the way I usually write it, or you can write it like this, right? Alright, so let's talk about the equilibrium constant, because it's all about developing an equilibrium expression or the constant that tells us what the ratio of reactants to products is, or vice versa. Okay, so think about it this way. If I have a forward reaction, what kinetics tells me is that the rate law is going to be this K sub F for the forward reaction, my small k for the forward reaction, is going to be my concentration of my reactant here, right? It's got a one coefficient, so there's no exponent here. If I were to take that same equation and write the reverse reaction, I take the product now, it becomes the reactant, and I write the rate law for that one, the reverse reaction, I get NO2 squared, right? Because I've got 2 NO2 here. Now if I take those two together, at equilibrium, what I'm saying is my forward rate and my reverse rate are the same, which means my equilibrium or my rate expression is the same for the forward and the reverse. they're equal. Okay? So if I were to rewrite this, we end up with the rate constant of the forward over the rate constant of the reverse is equal to the products, right, with their exponent over the reactants with their coefficient as the exponent. Okay? So this ratio of rates is what we know as the equilibrium constant. Okay? And it's actually a big K. So the big K, or the equilibrium constant, is the rate of the forward over the rate of the reverse. And it is the concentration of the products raised to the coefficient over the concentration of the reactants raised to its coefficient. Now you'll see the symbol written differently, but this is a capital K, whereas these rate constants were small k's. So you'd see it sometimes just as K, or you might see it as K because these are concentrations as K sub C. So if we consider the general reaction, these are coefficients, these are reactants, these are products, then the equilibrium expression for any reaction would be it's the products raised to the exponent that matches their coefficient over the reactants also raised to the exponent that matches their coefficient. Okay? So let's take a look. Let's write the equilibrium expression for these. Alright, so let's write the first one. So the first one's going to be, I have my K sub C is going to be my oxygen, and I want it to the third because there's a coefficient there of 3, over ozone concentration, the bracket means concentration, to the second. Okay, here my Kc is going to be my product, and I need to raise it to the second power, over my reactants. The NO has a 2, and my Cl2 has a 1. Okay, and lastly, here we'd have Kc is equal to my product, coefficient of 1, so there's no exponent, and my silver concentration, I need to put these in brackets, right, times my ammonia, and that is going to be raised to the 2 because of this 2 here. Okay. So you can try that one, and that would be the answer. Do that on your own. Okay, so in addition to writing the equilibrium constant for concentration, I can also write an equilibrium pressure equation. Okay? And that is, we know that the pressure is proportional to concentration. So remember this. So if I were to have let's say a gas in a closed container, let's say I have 2 moles of gas, and I somehow in that closed container pump in 2 more moles of gas, that looks like a sad face or a mad face, then my pressure doubles, right? So pressure, when you're talking about a gas, is also an indication of the how far a reaction has proceeded, right? So here I could take the pressure. Remember, we have A plus B gives me C plus D. I still have my products on top, my reactants on the bottom. I'm not using concentrations here, so I can't use the bracket. I'm using pressures here, right? They're still raised to their coefficient. Same thing over the reactants. Okay, so remember the ideal gas law, Pivner, right? We can rearrange it and get pressure is equal to N over V times RT. And we also know that if we're talking about a closed container, then volume is constant. And we can rearrange that and get a relationship between Kc and Kp. And this is the relationship. Kp, equilibrium pressure, is equal to my equilibrium concentration times the gas constant, which we're going to use 0.0821, times my temperature in Kelvin, right, times change in N. Moles of reactant over moles of product. Sometimes it's easy to forget whether this is Kp equals Kc or Kc equals Kp. And someone has given me a valuable piece of advice, which is think about politically correct. P comes before the C. Alright, so we're going to take a look at calculate the Kp for this reaction. Okay, so Kp, as we just said, is equal to my Kc times RT to the change in N. Okay, my Kc is 9.60. My R is 0.0821. My T is in Celsius. I need to make that Kelvin, so it's going to be 573. This should be times 573, and this whole thing is going to be raised to the power of change in moles. So I start with 3 plus 1 is 4, and I end up with 2, so the change is minus 2. Okay, so let's take the calculator out and calculate what that's going to be. Alright, so I'm going to take, turn it on, clear it, 9.6 times, I'm going to put in parentheses, 0.0821 times 573, close my parentheses and put that to a second EE negative, whoops, it's this, it is not a second EE negative 2, my bad, this is a common mistake, and I should not have made this mistake. I'm going to delete that and delete that. This is raised to the minus 2 power. This is not EE minus 2. It's not 10 times 10 to the minus 2. This is raised to the minus 2. So I'm going to do caret minus 2. And when I do that, I get 0.0043, which matches this. And one of the really, really nice things about equilibrium constants is they have no units. This is one of those units where you don't have to worry about units. Didn't mean that as a pun, but okay. Let's take a look at another. Alright, so here we wanted equilibrium expression in this equation is 1 times 10 to the minus 30. We want to calculate K sub P. So again, a K sub P is equal to K sub T times RT times to the power of the change in N. And my K sub P is going to be 1 times 10 to the minus 30 times R, which is 0.0821, times T, which is going to be 25C, is 298. And my change in moles, I have 1 mole and 1 mole, so 2 moles of reactants going to 2 moles of product. My change in N is 0. So anything raised to the 0 is going to be 1. So this is the case where Kp will equal Kc. It's when my moles of gas are constant. Right? And that makes sense because the equilibrium constant is really looking at concentration of the products over the reactants. And if my pressure is constant, that would suggest that my number of particles is constant, right? My number of moles is constant. Okay, so you can get to equilibrium many different ways. You can start with all reactants. You can start with different concentrations of reactants. You could actually do the reverse reaction and start with products. Doesn't really matter how much you start with and what you start with. For a given reaction, your equilibrium constant is always going to be the same. So here I'm starting with reactant, and I end up with 0.213 equilibrium constant. Here I'm starting with product, different amounts of product, and I get to the same concentration. Now my concentration ends up being different at what equilibrium, but the ratio of the products and the reactants is going to be the same, which is going to be my Kc. Okay? Doesn't matter what I start with. I'm going to end up with the same equilibrium constant for the same reaction. Okay, and that's what, here's experiment 3, starting with some reactant. Here's experiment 4, starting with product, and what you can see is that they will end up the same place. Okay. This shows the same thing again. Doesn't matter where we start. We can start with reactants, or we can start with products. This is ammonia. In the end, once equilibrium is achieved, the ratio of the concentrations of these three is going to be the same. The actual concentration may change, but the ratio of the concentration of the three will be exactly the same. So what does K actually tell us? Well, if K is much greater than 1, it tells us the reaction is product favored, which makes sense because you know the K is putting products over reactants, so if this is a really big number, we're going to end up with more products when we're at equilibrium, right? And the converse is of course going to be true. If K is really low, then the reverse reaction is favored and we're going to end up having more reactants. Okay? So let's take a look at this. And we want to know, so the following diagrams represent three different systems of equilibrium, all in the same size container. Without doing any calculations, rank the three systems in order of increasing equilibrium constant Kc. Okay, let's do that first. Alright, so remember Kc, we are looking at, we're always talking about products over reactants, right? So here I've got, let's say, this is my reactant. I've got 4 of those. I've got 6 products. Here I've got 9 of those and 1 of those, and this is going to be 2 of those and 8 of those. So which one is more heavily product favored? Well, it's going to be this one. So it's going to be this one. And the least heavily favored is going to be this one, right? It's almost all reactant, and this is somewhere in between. So it's going to go from, my equilibrium constant is going to go from this to this to this. Okay? And then it says B, if the volume for the containers is 1 liter and each sphere represents 0.1 molar or 0.1 mole, calculate Kc for each system. Okay, so on the first one I'm going to have Kc equals my product. I've got 6 particles here, so it's going to be 0.6 moles over 1 liter. So it's going to be 0.6 molar over my reactant, which is going to be 0.4 molar, and that's going to be 1.5, right? No units on my K. Here I've got my product is going to be 0.1 molar, because I've got 1 particle here indicating 0.1 moles, and 0.9 molar for the reactant. That's going to be 0.11. I need 2 sig figs here, right? Okay, and here my product is going to be 0.8 over my reactant, which is going to be 0.2, and this is going to be equal to 4. Okay. Okay, so we can manipulate equilibrium constants in 3 ways, and let's talk about all 3. The first one is, here we have this equation, right? The equilibrium constant of a reaction in the reverse order is the reciprocal of the equation in the forward reaction. And that makes sense if we consider this, right? So I start with N2O4, make 2NO2. This would be my equilibrium expression, right? Product on the numerator. If I turn that reaction around, right, to do the reverse, I now have 2NO2 giving me N2O4. N2O4 now becomes my product on the top. NO2 with its 2 power becomes my denominator. So if I compare those 2 equations, they in fact are the reciprocal. Okay. Second thing is the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. Sounds like a mouthful. What does it mean? So here again we have the same equation, right? We write the equilibrium constant, it's products over reactants. If I were to take that equation, this whole equation, and multiply it times 2, I get this, right? Now I write my equation, and my NO2 is my product. It's now raised to the 4. My N2O4 is my reactant, now raised to the 2. And if I compare these two, what I see is this is the same as this raised to the 2 power. Okay, so that's why that works. And the last one is the equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. Okay, so let's take a look. The first one is saying is we calculate the value of K given the information above using the Haber process. So first we always have to write a balanced equation, right? So I have nitrogen and hydrogen gives me ammonia, right? Because I know what the Haber process is now. I have to balance, so I need 2 of those, which means I'm going to need 3 of those. Okay, so when I write the equilibrium expression, it's going to be Kc is equal to the concentration. Now you should always write the equation, this needs to be to the 2, on the AP exam first. And that is because even if you get the rest of it wrong, you put in the wrong numbers, you punch the wrong keys, you will get points for putting the correct equation. Okay? So it's always valuable to do that. Alright, so I'm going to take NH3's value, and this should be 3.1, right? So 3.1 times 10 to the minus 2, and that's going to be squared, over N2 is going to be 8.5 times 10 to the minus 1, times H2 is going to be 3.1 times 10 to the minus 3, and that will be cubed. Alright, so let's take the calculator out and give this a whirl. I'm going to put an L here for last time. Alright, 3.1 second EE negative 2, whatever that is, I'm going to cube it, or square it, okay? Let's square it. Alright, divide by, and I over parenthesize, I'm going to, this is 0.85, 0.85, close my parentheses, I want that, times, open my parentheses, 3.1 second EE minus, whoops, 3, whoops, that's a comma, that should be second EE minus 3, okay? I'm going to close that parentheses, raise that to the 3, to cube it, move my arrow over, which says I'm done with the exponent, close the exponent, and 1, 2, 3, 4, I should have 2 sig figs, and it comes out where it should, 3.8 times 10 to the 5th, or 10 to the 4th. There's no units. 1, 2, 3, 4, 10 to the 4th. Okay. Whew. Alright, now I want to calculate the value of the equilibrium constant for this, which looks exactly like the reverse of what I had. Okay, so let's take a look. So it's going to be 1 over, or just the reciprocal of that, right? 1 over that, so I can just take that number and say x minus 1, and I get 2.6 times 10 to the minus 5, which is what's right here. Okay. Now what I have here is calculate the value of the equilibrium constant for this. Now this is exactly 1/2 of what I had here. Okay? So if it's 1/2, I can raise this to the 1/2 exponent, right? So it's going to be 3.8 times 10 to the 4th, and I'm going to raise that to the 1/2, or the 0.5, right? So if I go up, and I take that, and I caret that to the 0.5, I get 1.9 times 10 to the 2. Alright, cool. Alright, let's take a look at a couple more. Alright, so gives us an equation, rate constant, write the equilibrium constant for the reverse reaction. Okay, so it's just going to be 1 over 1 times 10 to the minus 30, which is going to be 1 times 10 to the 30. Okay. Alright, this is a nice one. Given the following information, determine the value of Kc for this equation. Okay, so we have these with these equilibrium constant, and we want to find the equilibrium constant for this equation. Okay, so 2HF, okay, it looks like it might be double of this. Let's just make sure I got 2 H's and 2 F's. Okay, so what I'm going to need to do is take this, and doubling means I have to square this, right? And here I have H2C2O4 going to 2H4. So the H2 is here. Looks like this is just the reverse, 2HC2O4. Okay, so this is going to be, for this one I'm going to use 1 over this, right? And I'm going to take both of those and multiply them times each other because it's the product of the two, right? Alright, so let's do that. So I'm going to take 6.8 times 10 to the minus 4th squared times 1 over 3.8 times 10 to the minus 6. Okay, so let's get the calculator up. Let's clear this baby. So it's going to be 6.8 second EE minus 4, whatever that is. I'm going to square it, right, x squared, and I'm going to divide by 3.8 second EE negative 6, and when I do that I get 0.12, and there are no units. Nice, no units, I like that.